So in this talk, we'll be discussing our paper, namely Versatile Perceptual Image Compression with Diffusion Rendering. I'm Tongda, which is the speaker, and I'm also the author of the paper. We are a team from Tsinghua University and Microsoft Research Asia. In sentences, this paper is about how to construct a perceptual codec that works very well for both the screen contents and the natural images. And from the examples, we can actually see that our codec actually deals with the text content of the screen images very well, and also it also works pretty well for the natural images that do not contain text. So we'll be discussing the several ideas mainly. The first one is about the optimum coding principle for the perceptual and screen or machine vision. The second one is how to basically achieve a really naive implementation of this optimum coding framework. And we'll discuss our enhancement of the framework based on three levels: the domain level, adapter level, and instance level. And we'll also be presenting our experimental results. So let's get started with the optimum coding solution for the screen or the machine vision. So let's first discuss the notation needed for this paper. So we denote the source images as x. We denote the code for the x as y equals to fx, where f is the encoder. We denote the reconstruction image as x hat equals to gy, where g is decoder. And we also describe the setting of the screen coding or the machine vision coding. So there is some information z that can actually be determined from x. So we're really sure about the z given the source image x. For example, there exists some function that is deterministic, and we will have z equals to hx for some kind of deterministic function. So there is nothing blurry or really nothing uncertain we are about the z given x. So the target of the screen content coding or the machine vision coding is that we want to preserve the information z even from the reconstruction x hat. So we want to determine the z in a really certain and correct way even from the reconstruction image. So how to achieve this? Well, we provide a way that is one of the optimum coding rule for the screen or machine vision coding. So we first encode the z in the lossless way, and then we encode y with z as a condition, and then we decode z in a lossless way, and we decode y with z as a condition. But this framework seems to be really naive, and there are actually other works that use join coding or some kind of loss function that's related to the inference of z. So is our naive framework really optimum? And actually, this is already optimum coding framework. So if we want to preserve the information in z fully, then it is fully determined by y, or to say, we will have the entropy of z condition on y is 0. And then the code to jointly code z and y together is equals to encode y and encode z condition on y, and as the second term is actually a 0 term, then it equals to y. So we have hy equals to hy condition on z plus hz. This means that if we are to encode the latent independently, then this independent latent already contains the same amount of information of z inside. So it's equivalent to encode z in a separate way, and then we actually encode y condition on z. So this is actually formally described in theorem in our paper, Conditional Perceptual Quality Preserving Image Compression. It's another paper. So to this end, we know that the join coding or the loss function preserving that actually squeeze the information z owing to y achieve the same effect as encode z and y separately. So what is the coding rule for the perceptual quality and the screen contents or the machine vision altogether? So we use the perceptual quality definition following the perception distortion trade-off paper, which means that the marginal distribution of x is equals to the marginal distribution of reconstruction x hat. But why is this definition? Well, this is because if you give a human two images, one of the source images, another one is the compressed images, and you tell the human being to actually tell the difference between the two images, and they have a successful rate to guess which is which. And the successful rate is actually 0.5 plus 0.5 multiplies the total variation divergence between the marginal distribution of x and marginal distribution of x hat. So if people just cannot tell the difference between x and x hat, the successful rate is 0.5, and at that time, we'll have the total variation divergence 0, which means that these two marginal distribution is equals to each other. And how to achieve this? Well, this is actually relatively easy. We do not consider too much about the distortion. We can actually train a conditional generator model as a decoder, and we'll have the x hat, which is equals to the decoded images, and it should be equals to the posterior distribution of the source image condition on y and z. And this will actually lead to the marginal distribution of x hat to be equals to px. This should be pretty easy to verify. And so now we have the principles explained and why our principle is actually optimum for both the string coding and for the perceptual quality. And then we'll just announce a really naive implementation of this optimum coding framework to achieve this perceptual quality and screen content framework. So the first step is that we use an OCR algorithm to extract z from x, and we'll encode the coordinate in an exponential Colombo code, and we'll encode the text with a lossless compressor named Simix. And the second step is that we'll train a model which is a really state-of-the-art image compression model named MLIC, and with the text z as a condition, and we just optimize the written distortion target of this model, which means that we just optimize the bitrate and the mean square error. And then we actually use this model to encode y, which is conditioned on the lossless version of z. And during decoding, we will first decode the text information z out from the bitstream, and then we'll decode the y out, and then we'll decode the x hat out. This x hat is a reconstruction of MLIC. And the third step during decoding is that we will train a conditional diffusion model with z and y as condition. We actually want to learn a posterior x condition on y and z. And this step is actually where our name comes from, diffusion rendering. So the diagram is very straightforward. So there's only one term that needs some explanation, namely graph. So graph is just a rendering of the text, location, and content, and it is used just using a Python image library, PIL draw text. So this actually helps the diffusion to learn the rendering of text better, because there are just papers saying that diffusion model cannot just render text very real, it can only deal with local information. So we need this way to actually guide the model to actually know the text. So the diagram is, we have a source image x, we extract the text information z, we render the z into the graph, and along with the compressed image that is optimized in a mean square error pattern, we combine them together, and we use an algorithm named diffusion rendering to combine them into the final reconstruction. And the interesting thing is, the actual graph of z actually contains the location information and the content information of the text, while in the compressed image, it actually contains the color information, it contains the font information, it contains the alignment information. So we are sorting out like adding those two information together to fuse them into a final reconstruction with correct location, correct text content, correct fonts, correct text color, and even correct alignment. So the final result is actually pretty interesting. And the naive implementation does not really work empirically, and actually we will show later, it will have really severe color driftings from the source images. So we propose actually 3 levels of improvements. First one is domain level, the second one is adapter level, and the third one is instance level. So the domain level improvement means that as we are actually training a diffusion model from a pre-trained stable diffusion model, which is a text-to-image model. So this text-to-image model is actually not really prepared or trained for the screen content. So we actually train a LoRa adapter to adapt the original stable diffusion model to generate the screen contents better at the first place. So we will construct a prompt such as a screen content image showing something, and this showing something is actually the OCR content. So as shown in the images example on the right, so after LoRa fine-tuning, our stable diffusion model is actually able to generate a more screen content-like image. However, without the LoRa fine-tuning, our stable diffusion model will actually generate something more like a poster. So the adapter level improvement is just nothing more than combining several existing adapters, and let them to process different kind of information. For example, the control net is not really good at processing low-level information, but it's doing pretty well in processing a high-level information such as graph. And the stable SR is just designed for processing low-level information such as compressed images, but it's not that good at processing the text information. So we sort of just combine them together and let them to process different information source. And we also introduced an inference technique named instance level improvement. And this part can be really complicated, but it actually drastically improves the color drifting problem. So during the inference, we combine the instance constraint as a paper, namely idempotency and perceptual image compression. And we also add a new constraint using the OCR loss as an operator. This can actually be found with more information in diffusion posterior sampling for general noisy inverse problems. And so our three levels of improvement can be summarized as the right images. And actually, the domain level improvement is actually achieved with the LoRa. And the adapter level improvement is really a combination of the control net and stable diffusion, and also the stable SR. And everything is actually conditioned through a split layer, which is actually, I think, of a round of the GAN age that when people are doing semantic segmentation to image generation. And this split layer is actually shown to be much more effective than the control net residual addition. And we also add an instance level improvement. So originally we actually sample using the DDPM procedure, and now we add the diffusion posterior sampling guidance for both the idempotency constraint of the codec, but also the OCR part. And so this framework can actually also be simplified to adapt to the natural images. If we remove the domain level improvement, which is here, and we just remove the OCR guidance of instance level, which is here, and we just remove or we just clear away the glyph input using the text information. And so we can actually simplify this codec into a natural image codec, and it still works pretty well. So how does the three improvement works? Well, let's first see how does the baseline works. So the A is actually the baseline. We can see that for A, the text information is not that really, oh no. So the A is actually the just a post-processing of the MLIC images. So we do not actually have any condition of the text information for A. So we can see that there is some interesting results shown. The images is actually sharper, but we do not actually know the real text information because MLIC is not really good at preserving text information, and everything just becomes unreadable from this newspaper script. And the B is actually the naive implementation. We can see that the text information is actually really nicely contained, and the result is a lot better than A. However, we'll still have some really severe problem in terms of the color drifting, because originally we'll have a white paper, and now we have a gray paper. And C and D are just different ways for the adapter level improvement, and we can see that by combining the advantage of the control net and stable SR, we are already able to achieve a somehow very nice reconstruction. But still, along with all the other improvement, for example, the domain level improvement and instance level improvement, our final result is already really similar to the source, even at a really low bitrate. And we have a really nice metric showing a really high text accuracy and a really good perceptual quality. And there are other comparison to other different approaches that are actually designed to preserve the text. So you can actually see that the original MLIC without text information preserving, even if we actually increase the bitrate, to the other codec which contains the text information, is still not really good at preserving text. Because this is because the text is just not a target of MLIC training. It is just trained to optimize the rate distortion target, which is the mean square error. And there are also a large amount of papers that use a region of interest coding, which use a detector head to detect the location of text and adding this loss to the training of MIC. So in this way, we can actually improve the text quality, but without drastically improving the bitrate, we can actually not do a big change because there are just too many texts here. And there's actually another really innovative paper which uses the OCR result, or the logic of an OCR network as a loss function, which is also presented by Microsoft. But this part actually drastically increases the bitrate, which is not so desirable. And there is also approach that directly render the text onto the original images. This actually provides a lot of improvement for the text information accuracy. However, this is also really harmful to the other metrics, for example, the FID or the video result. So although it looks better for machine, it does not really look pleasing for human being. But our approach that renders the compressed images and the text graph picture can actually produce a really nice result, both visually and in terms of metrics. And also, comparing to other codec, our codec is the only one that is able to achieve both really high text accuracy and a really high visual quality, which is measured by FID and DIST, those perceptual quality, at the same time. So we perform experiments and evaluation on 2 screen content dataset and 2 natural images dataset, which are common, and we compare ourselves to a different type of codec, mostly the perceptual optimized codec, and it's shown that our approach is actually better than Perco, which is previous state of the art of the natural image codec, both in terms of the natural images and also in the screen images. So here are some useful resources. If you want more information about the paper, you can actually email me, or if you're Chinese or have a WeChat account, you can just contact me via WeChat. And I also list some reference paper which can be helpful for you to refer to the contents that I previously discussed. This include how to construct optimum machine code and how to construct optimum perceptual codec, also the diffusion control, graph rendering, and diffusion guidance, and mean square error optimized codec. And thank you. That is the introduction.